we can answer as many as possible. So I think we'll go ahead and get started. I'd like to introduce Leggy Arnold, who is a professor at the University of Wisconsin-Milwaukee in the Department of Chemistry and Biochemistry. Leggy's group is using the ion flux automated patch clamp system to evaluate small molecule efficacy in modulating calcium flux on the Gaba receptor. So I'll turn the presentation over to Leggy, and we will get started with the webinar.
Developed an assay to determine the Gaba receptor subtype selectivity in order to determine this for new benzodiazepines which were developed by our collaborator. So the outline for today is I want to give you a short introduction, and then the first part of my talk will be about the automated patch clamp assay, and we are using for that transient transfected hexagon-3 T cells. And we were investigating an agonist Gaba and the positive modulator H3166. And then in the second part of my talk, I would like to address some technical aspects of the automated patch clamp assay. So I will address like the success rates, the transfection protocol we developed, as well as our developing time. So the Gaba receptor is a ligand-gated ion channel, and the small molecule gamma-aminobutyric acid actually inhibits the signal transduction by increasing the chlorine flux into the cell, which is also called hyperpolarization. This phenomenon is seen in GABAergic neurons, and the majority of neurons are GABAergic. That means they can actually produce the neurotransmitter and can actually which inhibits the communication between two neuron cells. The Gaba receptor itself is a pentameric membrane receptor, and I just depicted that in the little figure here, where you have the closed receptor arranged in a circle, and in the presence of Gaba, the receptor is opening and increases the chlorine flux into the cell and increases the negative potential. Although there are 19 gene products known of the subtypes of the Gaba receptor, the most common one is the alpha-beta gamma combination in the brain. And in order to manipulate these particular receptors, benzodiazepines have been developed a long time ago, and these molecules can modulate the combination of the alpha-1 to 3 and the alpha-5 together with the beta-3 and the gamma-2. These different receptor combinations have an important pharmacological effect, and this is what I summarized here at the bottom of this slide. The alpha-1 is known to modulate sedative and hypnotic effects. If you're looking for an anxiolytic or an anti-anxiety compound, then you would like to have the benzodiazepine selectively modulate the alpha-2, alpha-3, and alpha-5. And if you're looking for a compound which is sedative, then you would like to increase the efficacy for the alpha-4 and the alpha-6. So by dialing in the selectivity towards the different subtypes, we can influence the pharmacological profile of the benzodiazepines. The most known by the benzodiazepines is probably diazepam, also known as Valium, which was developed a long time ago. But this compound is actually relatively unselective regarding the alpha subtypes. And so I'm collaborating with Dr. James Cook here at the University of Wisconsin-Milwaukee, and he worked over 30 years developing new benzodiazepines, and he has a very successful compound which is called HZ166. And this compound has a reduced activity for the alpha-2 and the alpha-5. So it has an increased activity for the alpha-2 and alpha-3, and is therefore a very good anti-anxiolytic with non-sedative effects. Our collaboration is also stretching forward from here on because we are interested to profile new compounds coming out of his lab in order to determine the efficacy for the different subtypes of the Gaba A receptor. We are also working together with Professor Werner Siegert from the Medical University in Vienna, and he is using a Manual-Electrode voltage clamp assay in order to determine the activity from benzodiazepines. And this is a manual assay where frog oocytes are clamped, and then we have a manual compound application in the range of 10 to 15 seconds, and the medium peak current can be recorded after 2 and 3 seconds. And our collaborator was sending us the plasmids for the different alpha subunits 1 to 6, and the beta 3 and the gamma 2 subunits, and we used these plasmids in order to develop an automated patch clamp assay using transiently transfected HEC293 cells. So for that purpose, we purchased the IronFlux, which is an automated patch clamp instrument, and I depicted in this picture over here. You can see it's pretty much a benchtop instrument. It operates like a plate reader. Indeed, we are using multiple plates in order to carry out this assay. The instrument was affordable, and it gives us very high performance data for the assay we are doing. But I just want to mention that this instrument is not only capable to assay the Gaba A receptor, but all ion channels in general. So the important features of this instrument are that it's multi-ball plate based, and so we have 96 or 384 ball plates, which in the bottom are connected, I point this out here, through a microfluidic system. And this plate is divided into ensembles, and these ensembles, as depicted on this slide, consist of 12 interconnected wells, and these are the 12 wells over here. 8 of them are used in order to apply compound to the patched clamp, the patched cells. Then we have 2 trapping zones where the cell is patched and then in and out in order to apply a new compound and flush the system. And these are overlying like this, so the microfluid system is interconnecting the different wells. The fluidic control is based on pneumatic pressure. Once you insert the plate into the instrument, it will be sealed from the top, and when you apply pressure on the top of your liquid, it is pushed through the microfluid system to the trapping zone. So the trapping zone was very important for us because this, the IronFlux instrument is one of the few instruments which can actually tramp multiple cells, 20 cells to be correct, and this is depicted in this gray picture here. We have all the 20 cells are individually patched by one trapping zone, and we have one trapping zone here and the other one trapping zone over there. So we are actually patching 40 cells for each ensemble, which gives us a very high success rate and also enables a high integrity seals, and we have a very minimal variability in the data we are recording with this instrument. The using transient transfected HEC293 cells have some advantages and disadvantages. The advantages here is we have a very high flexibility by using different plasmids. We have a high transfection efficiency using our transfection reagent. We are also, after we transfect our cells, we can freeze them and then thaw them when we want to use them. They have a relatively low cost, and we can also omit antibiotics if you compare that with stable transfected cells. The disadvantages here is that we have to transfect 3 different plasmids. So there is a degree of heterogeneity in this assay. Also, the absolute currents for the ensembles can differ, but the relative relationship is always the same. And we also think that maybe the reagent can weaken some of the cell membranes. So what I want to show you today is, in the first part of the talk, is a comparison between our automated patch clamp assay and a manual 2-electrode voltage clamp assay, which was carried out in the laboratory of Professor Siegert. So for the automated patch clamp, we are using HEC293 T cells. We are patching in one trapping zone 20 cells. We have a fast compound application, but a relatively limited amount of receptors regarding the size of our cells. In comparison with the manual assay, which use oocytes, and this is a single cell assay, we have a manual compound application, but we expect that we have a larger amount of receptors because these cells are bigger than the HEC293 T cells. So what I show you here is the first piece of data where we have the alpha-1, beta-3, and gamma-2, Gaba-A receptor, and for the manual 2-electrode clamp assay, we see an AC50 of around 47 micromolar, and with our automated patch clamp assay, we find EC50 of 1.1, which is closer to the reported value in the literature from Böhme in JBC in 2004. If we look at the sweeps, we find a very nice response regarding an increasing amount of GABA and a saturation at higher concentration of GABA. For the alpha-2, we find an EC50 for the manual patch clamp around 19 micromolar. In our assay, we find an EC50 of 1.2 micromolar. That's a little bit tighter. And if we look at the sweeps, we see here that in relationship with the alpha-1, we find a smaller response to an increasing amount of GABA, but still we have nice saturation at higher concentration. For the alpha-3 Gaba-A receptor, we find an EC50 of 80 micromolar for the manual assay, and the automated assay, we find an EC50 of 1.9 micromolar. Also in this case, we see that the sweep response is very robust and comparable with the alpha-1 unit containing Gaba-A receptor. The alpha-4 unit, for the manual assay, we find a relatively shallow slope. The hill slope here is 1.7, and the EC50 is 20 micromolar. In our automated assay, we see that the hill slope is higher, and the EC50 is also significantly lower. Regarding the sweeps here, we find a similar, smaller increase of the negative current, which is comparable with the alpha-2 subunit. Then the alpha-5, we find EC50 of 8 micromolar, which is the smallest EC50 for the manual assay. And for our automated assay, we find an EC50 of 1.3 micromolar for GABA. And also here the response is relatively small in comparison with the alpha-1 or alpha-3. And last but not least, the alpha-6 beta-3 gamma-2 containing Gamma-I receptor has an EC50 of 15 micromolar for the manual assay, and for the automated assay we find an EC50 of 0.23 micromolar, which is closer to the reported 1.0 micromolar in JBC in 2004. So also here the sweep has a very nice dose response comparable with the alpha-1 containing receptor. So now I want to switch gears and talk about a little bit the kinetics. And what I show you here is the normalized current response in relationship to the time at a GABA concentration of 3.7 micromolar. And I just overlaid here the sweeps for the receptors, Gaba-A receptors, bearing different alpha subunits. And what you can see is that most of them are overlaying very well, except the alpha-3, beta-3 gamma-2 containing Gaba A receptor. So I want to point out first, before commenting on the kinetics here, that the kinetics really depends on the assay you are doing. So for instance, there is a publication from Haas from 1999 where he was using an outside-out assay and 1 millimolar GABA, and here the activation was seen in up to like 1 millisecond, and the deactivation took as long as 1 second. So in our case, and with our conditions, we find that the activation takes for all except of the alpha 3 subunit containing receptor 1.1 second, whereas for the alpha 3 one is 1.6 second. And the same trend we can find for the desensitization, where the alpha 3 containing Gaba A receptor takes longer to desensitize. So we can make a relative comment on how the activation and desensitization occurs within the Gaba A receptor having different alpha subunits. So in the next part of my talk, I would like to show you the data we obtained by using a positive modulator, HC166, which is based on the benzodiazepine scaffold. This assay was carried out at a GABA EC3 concentration with an increasing amount of the positive modulator. And what we see here is a potentiation of the initial Gaba A induced current. So for the alpha 1, beta 3, and gamma 2 subunit containing receptor, we find an EC50 of 1.26 micromolar and a potentiation of 230%. And in our assay, we find a very similar EC50 and a very similar potentiation. So in this case, the automated and the manual assay data are in agreement. These are the sweeps, and what we can see here, if we increase the amount of the positive modulator in the presence of a small amount of GABA, we see an increase of the negative current. For the alpha 2 containing Gaba A receptor, we find an EC50 in the manual assay of 0.44 micromolar and a potentiation of 400%. And we see a similar trend with our automated assay, although the potentiation is not as big as seen as for the manual patch clamp assay. Regarding the alpha 3, we also find an increased potentiation for the manual patch clamp assay, manual 2-electrode clamp assay, and for our automated patch clamp assay, we find also an increase in the potentiation. And last but not least, for the alpha 5, we found that both series, the manual 2-electrode voltage clamp as well as the automated patch clamp assay, give very similar results. So I just summarized everything in this table, and what we can see here as a trend is that the automated patch clamp data seems to be a lower EC50 in comparison with the 2-electrode voltage clamp. But I also looked in the literature and compiled, which I depicted here at the bottom of the sheet. And what you can see is that the data in the literature has actually a wide range, and both of the data I showed you today are actually falling within this range. The second importance here in this table is that the data we obtained with the automated patch clamp assay are comparable with the one we obtained with the manual 2-electrode clamp assay, where the emphasis here is a higher potentiation for the alpha 2 and the alpha 3 subunit containing receptor. So in the second part of my talk, I would like to address some technical aspects. First of all, success rates. And what I show here actually is a screenshot from the IronFlux software. And the different colors are representing different ensembles. And what we can see here is that the absolute value of the induced negative current for each ensemble is different. But the relative relationship, that means the calculated EC50 value, is the same. And I just depict here an Excel slide where you can see that the dose response of each of the ensemble is the same. Also, the absolute response will be different. I also want to show you like another example where it's maybe a little bit clearer. So we can see here that we have a high response in some ensembles, and other ensembles the response is significantly smaller. But all of them show a very nice dose-response relationship. So now I want to give you some pointers on how we optimized our cell preparation, and that was very important for us to get these good results. So first of all, we are coating all our culture flasks with matrigels. So that makes the cells attach more quickly, and once we are applying the transfection reagent, the cells are also staying attached. We are only doing bulk transfections. That means we are transfecting in the culture flask itself, and therefore we are using lipofectamine, and we are not exchanging the media after a certain amount of hours. So it's just the transfection reagent stays with the cells for a period of 24 hours. And with this method, we get a very nice transfection efficiency. We are using detection instead of trypsin because we have seen that our cells, that more cells survive this procedure by using this more gently product by Genlantis. We also figured out that we have to resuspend our cells in serum-free media. This is very, very important because any residual amounts of FBS compromise the results we are currently getting with our assay. Then we are using centrifugation and the resuspension in order to make sure that we get rid of additional cell debris or dead cells. And then we are concentrating our cells at high concentration in order to trap these cells in the ion flux machine as quick as possible. Timing is also important here. We figured out that the cells, or the whole protocol, should be done in 30 minutes to make sure that the cells are still viable once we start the application. So I want to give you some pointers about the assay characteristic. We are using the ion flux 16, and this instrument is based on a 96-well plate, and the acquisition time for us is around 60 minutes in total. We are using two modes. We can use 64 different compounds in a replicate of 4, or we can use the ensembles, the 8 different ensembles, to do dose response curves with, for instance, Gaba as the agonist. And in a 96-well plate, this will allow us to study 8 different compounds at 6 to 7 different concentration with a replicate of 4. For our modulator assay, we are also using the 96-well plate. Here we can have all the different alpha subunits containing receptors in one plate. These are 6, but we have still 2 left, so we can actually have 8 response curves at a concentration of 6 with 4 replicates. So this is probably for some of you very important, because we purchased the instrument in early spring 2012, and we could actually optimize our assay within 4 months. So this was a very short amount of time, and we were very surprised, but the instrument is very easy to handle. And as a personnel, I had one graduate student, and she had actually no background in electrophysiology, but she was able to pick up the assay very, very quickly. And we are now at a point where we can actually determine the subtype selectivity of benzodiazepines within 4 to 3 hours, profiling all the different Gaba receptor having the different alpha subunits. So for the conclusion, we think that the ion flux is a very superior alternative to the manual patch clamp assay. First of all, it's easy to execute. As I showed you, my graduate student was able to optimize this assay within a very short amount of time. We can run a lot of different assays, which allows us to, we have never done this, but we can actually run up to 10 plates a day. We get very robust data. We have a very high success rate, so the majority of our assays are successful and gives us a dose response or a response we are looking for. They are working with inhomogeneous cell population, which was very important for us because we are using transient transfected cells. We have a flexible compound addition, which allows us to apply the compound 1 time, 3 times, as many times as we want to. We also addressed, we can comment on the relative kinetic analysis, and because of the speed of this assay, it has also high throughput screening abilities. So at the end, I would like to thank my collaborators. First of all, Professor Werner Sieghardt and Joachim Rensdorfer for giving us providing us with the plasmids, and also providing us with the data regarding the manual 2-electrode clamp assay, and also our collaborator at the University of Milwaukee, Professor James Cook, who provided us with the small molecule HC166. And for sure, my graduate student Nina Wong, who did all the work which I presented here today, and for financial support, the University of Wisconsin-Milwaukee and the National Institute of Mental Health. And I also would like to thank you for your attention, and I'm happy to answer the upcoming questions. So let me look at the question and answer here. Okay, there's another question. What is the transfection efficiency you get from the leaving lipofectamine for 24 hours? I normally change the media and kept the cells healthy. We actually did a small study where we transfected luciferase-based plasmid, and what we saw is that by leaving the media in the within the cells for 24 hours, we could actually have an increased transfection efficiency in comparison with changing the media after 3 hours. And we don't really see a lot of cell death. And that is probably because we are using the new product, the lipofectamine LTX, together with a reagent. We go to another question here. Would you expect that the EC50 with the TEVC showed have been actually left shifted compared with the patch clamp assay due to a poorer solution exchange kinetic of the former system? Am I concerned about the huge left shift of the EC50s obtained? This is something we are still investigating, but I think regarding the literature, I wouldn't be concerned about that, because I think that the EC50 of Gaba is really depending on the system. I showed you here the difference between the manual and the automated patch clamp assay, but these are only 2 factors. It's also important, how fast the application is, what kind of protocol you're using for the transfection, what kind of instrument you are using, and I think all these different parts have an influence for your IC50. So I think if you want to compare IC50s, you really have to use the same instrument and the same conditions. But what we know is our assays are very reliable, so we can the graphs I showed you actually repeats of for one receptor of more than 40 different experiments, and the EC50 was the same for all the 40 replicates. Okay, I want to like switch. Okay. Okay, this is like a technical question. I will skip this, maybe for a little bit later. Okay, there's one question here about the resistance. Yeah, the resistance is calculated for all the 20 cells in total, and in general, we are not really reaching the giga-ohm seal here, but what we actually figured out that by monitoring the different resistance, that the resistance itself, the absolute value we are getting for each ensemble, doesn't really have to do anything with the performance of the assay. So there is no correlation about the higher resistance, the better gets the data. So there is no relationship between these two parameters. Okay. Okay, this is like a technical question. Oh, there's a new question. Okay. Can you give details of the scale of transfection, number of cells, and concentration when added to plate? Oops. What are typical seal resistance? And have you quantified rundown with multiple applications of the same concentration of GABA? Okay. Let me go for the last one first. Have you quantified the rundown with multiple application of the same concentration of GABA? Yeah, we are doing that actually for all assays. We are always applying the same concentration of GABA or the modulator, and we see that the response is the same for both applications. So we get a very good washout for the GABA, and then we can actually hyperpolarize the cells again with the same concentration of GABA, and we are also getting the same response. About the scale of the transfection, we are using normal culture flasks like P75s in order for the transfection, but we have also used the bigger ones, the 150s, for the transfection, and this will normally give us enough cells to do, depending on the plate you're using. I think the 150s we can do up to five plates. When the concentration we are using in order to add them to the plate is around 5 million cells per milliliter. So that's this really high cell concentration, but we are also getting the traps, the cell traps very quickly. And the typical seal resistance, I just already commented on this one. Have you checked the numbers of cells trapped? Yeah, we have. We run the instrument in order to trap as many cells as possible, but it's a time interval, and we cannot check each individual trap. We are just getting an average of all the cells trapped. In order to check the numbers of cells, probably you need a camera within the system. Yeah. See, that's I think the last question here. I think we still have a little bit of time. I can wait a little bit more if you want to ask more questions.
I think this might be a good point to stop, but I just wanted to thank you, Leggy, for giving that great presentation, and
thank you, Mike.
for those in the audience, If there's any further questions that we weren't able to get to, or if you think of something afterwards, feel free to contact us here at Fluxion or Lake directly, and I'm sure he'll be happy to address those offline. So anyways, thanks again to Leggy for the presentation, and thank you for everyone for attending, and feel free to follow up afterwards as appropriate.
Okay, thank you.